Okay, in this chapter we'll talk about some basic linear programming problems. In fact, most of these examples are dealing with graphical examples. We've already done several in the insert material, but I want to bring out something which is the importance of units. So I'll go through some examples and show that. Now, to connect this to the previous video, we've just finished saying or proving that if I have a function cx plus k defined on a convex polyhedral set, then the maximum and minimum value occurs at an extreme point of C. And this is the same thing we've seen in the insert material in 2 dimensions, that if you have some region in 2 dimensions defined by constraints, then all you need to do is find the corner points of the region, evaluate your function at those corner points, and the point that has the best value, the biggest value if you want maximum, or the smallest value if you want minimum, will be the point that maximizes or minimizes over that entire region. Just to remind you, this notation, Cx is not just a simple C times a simple variable x. This x is a vector. This C is a vector. So this is C1x1 plus C2x2 plus C3x3 and so on. And then here we have plus k, where k is just a real number. So you're just adding k to every value of the function. It just shifts the function up or down. It does not change the relative position or location of the maximum or minimum. So if you need a refresher on that, you can go back to the previous video. Alright, so linear programming problems down here. And here's a nice word problem. Automobile manufacturer makes automobiles and trucks in a factory that's divided into 2 shops. Shop 1, which performs basic assembly operation, must work 5 man days on each truck, but only 2 man hours on each automobile. Shop 2, which performs finishing operations, must work 3 man hours for each automobile or truck that it produces. Because of minimum machine limitation, Shop 1 has 180 man hours per week available, while Shop 2 has 135 man hours per week. If the manufacturer makes a profit of 300 on each truck and 200 on each automobile, how much of each should he produce to maximize the profit? Alright, so first thing you should ask, is this a maximum or minimum problem? And obviously it's a maximum problem, and you're maximizing profit. Okay. Now, what are the constraints? The constraints are on man hours per week in the 2 factories. You have 180 man hours per week in Shop 1, 135 man hours per week in Shop 2. So what we want to do is to put this information into some kind of standard form that we can always use and repeatedly, and then once we have the problem in the standard form, we turn the crank, plug the numbers into the computer, and get the solution. All right. So let's go down here. Now, if you remember, I said that what you're trying to maximize, profit. So there's a profit line at the bottom. So for maximum problems, you put your maximizing function at the bottom of this data box. It's also called a tableau. Now you also have constraints. There are 2 constraints I mentioned: the 180 man hours per week of Shop 1, 135 man hours per week of Shop 2. So those constraints are here, 180 and 135. Right? So now what we want to do is fill in the stuff in the middle. Now notice something. Notice that the units on these capacities and on these profits. The profits given were 300. It says $300 on each truck. So you should think about that. $300 on each truck means $300 per truck. The units of that 300 is dollars per truck. And this $200 for each automobile, the units on 200 is dollars per automobile. Right? Now, and that's what's listed here, dollars per truck and dollars per automobile. Now, what about the constraints? What are the units on the constraints? Well, that's explicitly stated. 180 man hours per week. So we have man hours per week on this capacity for shop 1, 135 man hours per week on this shop 2. Alright, so I've extracted the information we've talked about so far and constructed this box here. We're talking about making trucks and autos in shop 1 and shop 2. And profit is what you want to maximize. So I put profits down at the bottom. We had units of dollars per truck profit and dollars per auto. And we had capacities for shop 1 and shop 2 in man hours per week. All right. So these are the profits. Now what I'm interested in is the total profit. Okay. So the total profit, I can think of this box as representing the total profit. Now what are the units of total profit? Well, you'd say dollars. But in fact we're talking about profit on a weekly basis. So the total profit will be dollars per week. All right, now, in order to get the total profit, we're going to produce a certain amount of trucks and a certain amount of autos, and that will give us a certain profit. So our variables, we have variables that we need to specify by this problem. We need to specify how many trucks per week and how many autos per week. And you can verify if I take dollars per truck and trucks per week, I get dollars per week. So when I take this variable, which I could call x1, and then this variable, which I call x2, if I take x1 times 300, that's going to give me dollars per week due to manufacture of trucks. Same here. I have dollars per auto, and x2 is the autos per week. So if I multiply dollars per auto times autos per week, that's going to give me dollars per week. So I have dollars per week from trucks, dollars per week from autos, so that's the total dollars per week. All right. Now these same variables need to multiply the resource coefficients in order to get these units. So we need consistent units. We need to have units here that work with these variables. If I make a certain amount of trucks per week, then I'm going to have multiply that by this capacity, and then I have a certain amount of autos per week, and I multiply by this capacity, and I should get this. So let me think about what units I would have to have here. If whatever units I have here, let me just put that in red, right? So let me just highlight that here. The units that I have there are going to be what? Well, I have to have those units, which I'll write this way. So the units that go here times trucks per week should give me man hours per week. And again, he has the S1 here, but that just refers to the fact that this is shop 1. We're looking in the first line for shop 1. All right, so the question is, what units must I have here in order to make this work out? Well, the week is already okay, but the trucks have turned into man hours. So what we're going to have to do is multiply this trucks to get man hours. So if you think about it a little bit, what the units here have to be man hours per truck. So these coefficients here, in order to make this box work out, these units must be man hours per truck. So let me pull aside the curtain and see if that's correct. So in fact our inference was correct. Man hours per truck times the variable, which is trucks per week, is going to give me man hours per week. Now does this one also work out? Well, we have to have these units, man hours per auto times autos per week, also work out to be man hours per week. And you'll see that the autos cancel, and you in fact do get man hours per week. All right, so this constraint equation works with the units that we have put here. Now how about the second row? Well, the second row is the same as the first row. The first row deals with shop 1, Second row deals with shop 2. Remember, in this case, the constraints are going across. There's no constraint on trucks. You can make as many trucks as you want as far as the owners of the factory are concerned. You can make as many autos as far as the autos are concerned. But you don't have unlimited capacity. Okay, there's no limit on profits, there's only limit on capacity. The owner doesn't care how much profits you make. The more the merrier, right? Okay, so in fact you have the same units down here. So all of these units are completely consistent. Man hours per truck times truck per week gives me man hours per week, so I'm okay this way. And then dollars per truck times truck per week gives me dollars per week. So I have different units for the capacities and for the profits, but all of these things work out. So the variables that I'm going to look for have these units: trucks per week for X1 and autos per week for X2. All right, so that's how things work out. So I have this nice so-called data box or tableau expresses all of my information. Now this is for a maximum problem. Let's look for a minimum problem. And the upshot is going to be, if we set up the minimum problem right and display it correctly in this kind of tableau, we can lay it right on top of the maximum problem in some way. And we'll make that more specific in the next section. So before we go on to minimum problem, just note that this second way of representing the box really is the very same way of representing, only it's a little less junky. If I want to get the units for this 5, I take the margin, the row margin, divided by the column margin. So this 5 gives man hours per truck. This one gives this 2 is man hours per auto, and this is going to be man hours per week. If I want the units of this 300, I take this dollars divided by per truck. Okay, dollars per truck, dollars per auto, dollars per week. So having these margins here shows me immediately how to get the units. I take the row label divided by the column label. All right, and the variables go across. What are the units of the variables? Well, in order to make this work out to be a total profit of dollars per week, I have to multiply this number, which is dollars per truck, by a variable and get dollars per week. So if I want to multiply dollars per truck by something to get dollars per week, I'm going to have to multiply it by trucks per week. Same with this. If I have $200 per auto, in order to get dollars per week, I'm going to have to multiply by autos per week. And the same thing works out for these numbers. This one is man hours per truck, right? Man hours here, truck here. In order to get that to work out to a capacity, which is man hours per week, I'm going to have to multiply man hours per truck times trucks per week to get man hours per week. So when you set up one of these data boxes, you should think about the units and make sure everything works out. This is really a very elegant method of displaying the units. You just need to remember that the row goes in the numerator and the column goes in the denominator. Now, let me just point out one thing. Is I mentioned that the variables go across. So it's x1 times 5 plus x2 times 2 equals 180. x1 times 3 plus x2 times 3 equals 135. What does that, and then the profit is 300x1 plus 200x2. What does that remind you of? You said it, matrix multiplication. If I have this as a 2 by 2 matrix and my vector is a column vector with 2 entries, then the multiplication I just described is the multiplication of this 2 by 2 matrix times this column vector. And in fact, you can make a 3 by 2 matrix and multiply by this column vector, and you would get the profit coming out here as the third component of the result. 3 by 2 matrix times a 2 by 1 column vector would give me a 3 by 1 result, so that would give me this last entry here. All right, so let's go down now to minimization problem. All right, so here he talks about units also. Okay. All right, so this is kind of the same thing that I've talked about. So here I'm skipping down to the minimization problem, and as you look at this, you should be thinking that in fact this problem is sort of the flip side of the other problem. You're trying, instead of maximizing profit, you're trying to minimize costs, and well, you'll just see how things work out. All right, so a mining company owes, let me close this. Mining company owns two different mines that produce a given kind of ore. The mines are located in different parts of the country and have different production capacities. After crushing the ores graded into three classes, high grade, medium grade, low grade, there's some demand for each grade of ore. The mining company is contracted to provide a smelting plant with 12 tons of high grade, 8 tons of medium grade, 4 tons of low grade ore per week. Now you might be thinking, so what is that? Is that something to maximize, something to minimize, or is that a constraint? Well, these are giving requirements, so this is a constraint, right? It costs the company $200 per day to run the first mine, $160 per day to run the second. However, in a day's operation, the first mine produces 6 tons of high grade, 2 tons of medium grade, 4 tons of low grade oil, or the second mine produced daily 2 tons of high grade, 2 tons of medium grade, 12 tons of low grade ore. How many days a week should each mine be operated in order to fill the company's orders most economically? Okay, so here the type of problem is a little bit hidden in the language, but you're trying to fulfill the company's orders most economically means that you want to minimize costs, because there's nothing about profit here. Here's only talking about cost. This cost is something you don't want to spend, right? So you want to make this as small as possible. If this were profit, that'd be a different story, but since it's cost, you don't want to spend that. So if you remember this example, we had two coefficients that had to do with the profit function, or the function to be maximized. And then we had two coefficients that had to do with the capacity, or the limits of the system. So let's try to do the analogy for the minimization problem. Which coefficients have to do not with the profit function but the cost function? Those are these two, 200 and 160. Now the wrinkle is that with minimization problem, we're not going to put it on the bottom like we did with the maximization problem. We're going to put it on the side. All right, and there's a reason for that, but we'll get to there eventually. So the two cost function coefficients are 200 and 160, while the requirements coefficients, well, these are requirements, 12, 8, and 24 for the three different types of ore. All right, so if we look at this tableau here and just look at the margins, you have cost requirements here, and you have, you have costs here, and they're not cost requirements. These are costs of production here, and then you have your requirements down here. All right, so try to ignore these here for a moment, but we have the units here. So what are the units here? This is $200 per day, which is required to operate mine 1, and then that's what the M1 here is. And then this is $160 per day, which is required to operate mine 2. All right. Now, how about the requirements? You had 12, 8, and 24. You had 12 tons per week of high grade, 8 tons per week of medium grade, and 24 tons per week of low grade. So the units here are tons per week in every single case. All right. So now we should think about what units do we need in the middle of the box in order to make things work out. Well, in this case, we want to minimize the total cost. There we have costs for mine 1 and costs for mine 2, so we can put the total cost down here. Now, what about units of total cost? Well, total cost is going to be cost per week, because we're considering this system on a weekly basis. So this is going to be dollars per week. You're operating mine 1 and you're operating mine 2, and both mines incur some costs, and the total cost is going to be dollars per week. So notice that I have a little different setup here. In the maximization problem, we had certain amount of trucks to produce and a certain amount of autos to produce. And that gave us the capacity. So the variables went across for the maximization problem. For the minimization problem, it's more convenient to make the variables go down. So I'll call this V1 and V2. So the question are, what are the units of V1 and V2 in order to make this work out? I get V1 times 200 plus V2 times 160 to give me a number that's in dollars per week. So I need dollars per day times some units gives me dollars per week. Well, that unit is going to be days per week. Now he'd say M1 days per week, but the unit is actually days per week. And V2 also, the unit is days per week. So these are the unknowns. This is what we want to determine. And you can confirm that with the problem. The problem says, how many days a week should each mine be operated in order to fulfill the company's orders most economically? Those are the variables. That's what you want to determine. Now, what about these numbers here that I blacked out? Well, remember that these now are your constraints. Okay? So these units have to be consistent in order to get me this unit. So this unit times days per week must be tons per week. Whatever units these are times the variable, which is days per week, must give me tons per week. So I'll just put here variable times days per week equals tons per week. Okay, so what's the units here? Right? What units are we going to put here? Well, notice the difference, but we have week, which is okay, but the days has turned into tons. So here we're going to have tons per day. Tons per day. And let's see if we're right. So we'll just try to get rid of this and see. Voila, tons per day. Here we also have tons per day, tons per day. All right. So all the units are working out, and we can express this in the same way by putting the units in the margins. So let's go back and see how that's done. The units in the margins are here. Now in this case, the column units are in the numerator and the row units are in the denominator. Now that's indicated here when you say per day means that's 1 over day. And this is 1 over day, this is 1 over week. So per day, per day, per week. And you can verify that the units all work out if you multiply these units properly. All right, here you have 2. This 2 should have units of tons per day. This 12 should have should be tons per day. This number here should be dollars per week. So all of our units are working out nicely. Okay, so just one more example. This is taken from the exercises at the end of the section. 2 breakfast cereals, and they're vitamin B and iron, the 2 breakfast cereals here. And here you have Crix costs 8 cents per ounce and Crunch 10 cents an ounce. How can we satisfy the minimum daily requirements at minimum cost? You only need 1/3 minimum daily requirement because you don't just eat cereal in a day. This is just for your breakfast. So you assume your breakfast only satisfies 1/3 of your minimum daily requirement. All right, so let's go ahead and try to set this up in terms of units. So this is mg per ounce. Now this is a minimization problem. So remember that for a minimization problem, the numerator goes for the column, the denominator goes for the row. So we're going to have mg down here for the units here, and then here we're going to have per oz or per ounce here. Right? And you can see that those units work out. Now here we have, instead of per ounce, we have per day. Right? So far we only have the constraint information. Now what about the minimization information? Crix costs 8 cents per ounce, Crunch costs 10 cents per ounce. So obviously 8 has to go for Crix, 10 has to go for Crunch. All right, now I've already got the per ounce here, and this is mg. So the only units I don't have are the units for the dollars here, units for the column here. I said what it was. So what are the units for the column? I'm sorry, that's not profit, it's cost. Sorry, because this is a minimization problem. This is a cost problem. Okay. So what are the units for the column here? Well, the units are dollars. Okay. And that in fact you're going to get the total cost is going to be dollars per day. So these units work out. All right, so if you look at this and you just pull out the units, then you can see these boxes work. So try some others and see if you can make this work out. It's good to get some practice.